It's useful to pretend like all materials in the universe can be broken down into a category of insulator, electrical insulator, or electrical conductor. Now that's not completely true. There are semiconductors and superconductors and other exotic forms of electrical materials, but for most introductory physics classes and problems and tests, you can get pretty far assuming that it's either an insulating material electrically or a conducting material electrically. And before I talk about the differences between these, here I have two solid cylinders of either an insulating material or a conducting material. Before I talk about the differences, one similarity is that both insulators and conductors are composed of a huge number of atoms and molecules, and these atoms and molecules, whether it be insulator or conductor, are composed of a positively charged nucleus and a negatively charged swarm of electrons that surround that nucleus. Another similarity is that for both conductors and insulators, the positively charged nucleus cannot move. I mean, it can wiggle around and jiggle just from thermal vibrations, maybe a little bit in place, but it can't travel freely throughout the material for either an insulator or a conductor as long as it's a solid. If it was a fluid, I suppose these things could move and migrate around, but for a solid, the positively charged nucleus is fixed. They're stuck. The thing that might be able to move are the negatively charged electrons, and here's the difference. There are electrons in a conductor that can move about relatively freely. These can move around with almost no resistance. Whereas for insulators, the key difference is that these electrons cannot move around freely. These don't have the right energy levels and bands in order to make these electrons move around freely. They're also stuck. For insulators, everything's basically stuck. These electrons might be able to jump around in their own atom or get shared with a neighboring atom, but it can't jump around freely from atom to atom and travel throughout the insulator. For the conductors, the electrons can do this. That's the key difference. Now, the electrons aren't going to just do this on their own. They'd have to be compelled to start moving by hooking this up to a battery or setting up some sort of electric field or force. And if that did happen, then the electrons in a conductor could start migrating down the line. But in an insulator, the electrons are stuck, which might make you think that, well, okay, shoot, for electrical materials, all we really care about are the conductors. The insulators we just use if we don't want electrical interaction. And while that's somewhat true, it's not completely true, because if I set this insulator up to a battery, or I set up some sort of electric field or force in here, even though the electron in an insulator can't jump from atom to atom, what it can do is it can shift. This nucleus and the cloud of electrons can kind of shift a little bit. Positive maybe this way, and then the negatives over on the other end. So what you'd get is that overall, this side of the atom would be more negative, and this side of the atom would be more positive. And even though the electron doesn't move and the electrons don't move, now because this is set up where the positive is shifted from the negative, this material, if you get all of them to do this, or a lot of them, this can create an overall electrical effect where this insulator can interact with other charges nearby and exert forces on them. So even though the charges can't flow through an insulator, they can still interact electrically. Now, let's see what happens if we add extra charge to these insulators or conductors. I mean, the way they started off right here, we had just as many positives in the nucleus as there are negatives surrounding them, and that's true for the conductors and insulators. What happens if we add extra charge? Maybe we add extra negatives into here. Then what happens? Well, it'd get really messy if we tried to draw it with all the atoms. So since these all cancel out their overall charge, I'm not going to draw every atom and nucleus. I'm going to just pretend like those are there and they're all canceling out. I'm just going to draw the actual extra charge. So let's say we added extra negative charges to this insulator. What would happen? Let's say I just add a negative charge here and a negative charge there and here and there, and I've added a bunch of negative charges to this insulator. What would happen? Well, we know these negatives can't move throughout an insulator. Charges can't flow through an insulator, so they're stuck, which means for an insulator, I could charge the whole thing uniformly if I wanted to, where the charges spread out throughout the whole thing. Or I could make them bunch up on one side if I wanted to, and they'd be stuck there. But the point is that they're stuck. For a conductor, what would happen? If I tried to put a negative here and a negative there, some extra negative charge on a conductor, they don't have to stay here if they don't want to. And if you put extra negatives in here, they're not going to want to because negatives repel each other. Just like opposites attract, like charges repel. So what are they going to do? Well, this negative is going to try to get as far away from the other negative as it can. It's going to go over here. This negative is going to try to get as far away as it can. It repels it. Now, it can't jump off the conductor. That takes a lot more energy. But they can go to the very edge. And that's what charges do for conductors. If you got a solid conducting material, you put extra charge on it, it's all that charge is going to reside on the outside edge. Whether you've added extra negative or positive, always on the outside edge. So you can only add charge to the outside edge for a conductor, because if it wasn't on the outside edge, it'll quickly find its way to the outside edge because all these negatives repel each other. And I said this is true for positives or negative. You might wonder, how do we add a positive? Well, the way you add a positive is by taking away a negative. So if you started off with a material that had just as many positives as negatives and you took away a negative, it's essentially like adding a positive charge in here. But again, the net positive charge, the net negative charge always resides on the outside edge of a conductor because charges try to get as far away from each other as possible. So what physical materials actually do this? What physical materials are insulators? These are things like glass is an insulator, wood is an insulator, most plastics are insulators. All of these display this kind of behavior where you can distribute charge and the charge can't flow through it. You can stick charge on it. In fact, you can stick charge on the outside edge and would just stay there. And there's conductors. These are things like metals like gold or copper is typically used because it's kind of cheap, cheaper than gold certainly, and or any other metal, silver works very well. These are materials where charges can flow freely through them.
Here I have a circuit with a battery, light bulb, and gap. If I fill this gap with a metal, the light comes on. If I fill this gap with glass, the light stays off. You probably already know this because metal is an electric conductor and glass is an insulator. But what happens when I fill this gap with a silicon wafer? The light stays off, so you might think the silicon's an insulator. But what if I heat it up? Thank you. It lights up. The silicon is insulating at room temperature but conducts electricity when it's very hot. It's a semiconductor whose conductivity changes based on the environment. This special ability makes semiconductors the perfect brains for electronic devices. Circuits of small semiconductor switches, called transistors, are at the heart of computer chips and enable them to do math and run programs. Semiconductors have enabled electronics to become smaller, faster, and more reliable. But what is it exactly about these semiconductors that allow them to either conduct or insulate?
In this Easy Ed video lecture, we're going to learn what are conductors, insulators, semiconductors, the difference between intrinsic and extrinsic semiconductors, as well as P-type and N-type semiconductors. Now let's first understand the materials. When we talk about materials in electronics, we compare them to their current carrying capacity, and they can be classified into three types, namely conductors, semiconductors, and insulators. Conductors are materials that have excellent current carrying capacity or allow good flow of current through them, such as a copper wire. And semiconductors, as the name suggests, allows partial or semiconduction of the current, or we could say its current carrying capacity is in between the conductor and the insulator, such as germanium. Whereas insulators are materials that are bad conductors of current and do not allow the flow of current through them, as they do not have a current carrying capacity, such as wood. Now let's further understand this with an example of a stadium entrance and people. Let's imagine the stadium entrance to be a conductor and the people as current. Now we can see a large group of people passing through the gates and enter the stadium easily in the same manner in which conductors allow electricity to pass through them easily. However, here we see the crowd of people moving past the entrance one by one slowly in a queue. Now, why is that? That's because the current in a semiconductor passes through it partially but continuously. In the case of insulators that are bad conductors of electricity, we can see the stadium entrance, which we have assumed to be an insulator, is blocked, thus not allowing the crowd of people, which we have assumed to be as current, to pass through it. The term semiconducting was used for the first time by Alessandro Volta in 1782. However, the first documented observation of a semiconductor effect is that of Michael Faraday in 1833, who noticed that the resistance of silver sulfide decreased with temperature, which was different than the temperature dependence observed in metals.
We all know that electronic devices output heat, especially when they're working hard, too much of which can result in sweaty palms, melted chocolates, and even catastrophic failure. But do you know why? It's because the circuits and wires inside an electronic device don't conduct electricity perfectly. They have a certain amount of electrical resistance, which is the tendency for a material to resist the flow of electrons. This resistance manifests itself as heat and sometimes light. This is a good thing for something like a stovetop, electric heater, light bulb, or a toaster. Without electrical resistance, your toaster wouldn't toast, which would make it one of the world's least useful inventions ever. But most of the time, you don't want your electronics to heat up. Imagine for a moment that your house used tungsten wires. That's the same material used for incandescent light bulbs. Your whole house would burn to the ground. That's why most wires are made out of copper, which conducts electricity quite well and without much resistance. Aluminum, copper, silver, and gold are great conductors of electricity, but gold and silver are rare, so aluminum and copper are often used because they're less expensive. But even these highly conductive materials still don't conduct electricity perfectly, which is why electronic devices like computers get so hot. Without all those heat sinks, fans, radiators, and heat pipes, your computer would heat up so significantly that it would basically melt or catch fire. Electrical resistance is a big issue for pretty much anything that uses electricity. Modern power lines use thick cables and high voltage to reduce electrical resistance, but a lot of electricity is still wasted. It just turns into heat and floats away. If only there was a way to conduct electricity with absolutely no electrical resistance. That's what a superconductor is. Superconductors are able to conduct electricity perfectly, with no resistance and no heating of any kind, and they are so cool. Superconducting wires are used for things that require massive amounts of electricity, like inside MRI machines, power plants, and particle accelerators. And superconducting magnets look like something straight out of science fiction. Since they move only along their magnetic field and never against it, they can hover in the air indefinitely. Sounds awesome, right? But there's a huge catch. For superconductivity to work, you need incredibly low temperatures, near absolute zero, which requires the use of liquid nitrogen or helium. This greatly restricts how and where superconductors can be used today. That's why scientists have been working to create superconductors that work at higher and higher temperatures. If we had room temperature superconductors, modern technology would be changed forever. Remember all those heat sinks, fans, radiators, and heat pipes? With a superconducting computer, you won't need any of that anymore. Electronics would get smaller and use less electricity more efficiently. This is one of the great scientific advancements that I hope I get to see in my lifetime. Maybe we'll get that Back to the Future hoverboard after all. Anyway guys, I hope you enjoyed this episode.